and Physical Society. And as you know, this year has been a bit tough because of the lockdown and because we lose some of our members. But it is very good that we still can join and share together the physics. So I want to thank everybody as well as the organizing committee, because they did a very, very nice work. And I want to invite you as well to join us during the coffee breaks. There will be a session of several small rooms where you can join and ask to the speakers. And also, if you want to stay in the main screen, in the main session, I invite you to come to talk and to meet with colleagues, as if at least a bit as if we were together in a place. Well, the next, please, the next. So as you know, the mission of the division is to encourage graduate students and young postdocs to present their research work on high energy physics. This is a place where you can feel free to speak up and to present, to explain in a very friendly framework where you can discuss with the experts as a first approach to which will be your job as professor or researcher and so on. This year, as you know, the organizing committee is conformed by the Benemérita Universidad Autónoma de Puebla, de Centro de Investigación y de Estudios Avanzados del Instituto Politécnico Nacional, la Universidad de Sonora y la Universidad Autónoma de Chiapas. There you can find the links to our Zoom, to the Indico webpage, and also to the Facebook webpage, where we are going to be broadcasting all the sessions. Thank you very much, and I will pass the microphone, not, but the turn to Jose Benitez, who is the chair of the organizing committee. Thank you very much, and enjoy the meeting.
Muchas gracias, Karen. Thank you very much for that introduction to the meeting. So I will just present the program for the event. So here you can see the list of areas that are covered in this event, this annual event, and it includes the astrophysics, cosmology, neutrinos and dark matter, QCD and hadron physics, physics beyond the standard model, instrumentation, computation, and accelerator physics. We have electroweak and flavor physics and QFT. And we were able to get more or less 1 or 2 invited speakers per area, which you can see listed here. More or less 1 or 2 invited speakers per area, which you can see listed here. Okay, sorry. So we have in the first area, we have Dr. Tanguy Pierrot from KIT. Then we will have Dr. Arturo Menchaca from Instituto de Física UNAM in the dark matter area. Tomorrow we'll have Dr. Elena Santopinto from INFN at Genova in the area of QCD and Hadron, as well as Dr. Christophe Royon from University of Kansas. In the area of Electro Week and Flavor, we have Dr. James Olson from Princeton. In instrumentation, we have Dr. Gustavo Medina from Instituto de Ciencias Nucleares, UNAM. And then on the last day, we will have Dr. Alec Towsley Booth from Michigan and Dr. Shiking Shang, both discussing on the new results for the muon G-2. And finally, we'll have a presentation on rare decays and anomalies at LHCb from Dr. Mick Mulder from CERN. So here's an overview of the timetable of the event. So it's 2.5 days. Here, starting every day at 9 a.m. Mexico City time. For the areas that I just discussed, we will have the session conveners, which are listed here: Dr. Alberto Carramillana today, Alexis Aguilar, and Saul Ramos. Tomorrow, the sessions will be chaired by Dr. Alfredo Raya, Edward de la Cruz, and Isabel Pedraza. And the last day, the morning, will be chaired by Dr. Pablo Roig. So today, at the end of the day, we have the poster session for which the presenters have already posted their videos, so you can obtain a link to those playlists from the Indico. If you would like to watch those videos, they're very good. And then you can also come into the session here, and there will be dedicated rooms in Zoom where you can ask questions. Okay, tomorrow we also have the General Assembly of the division, which is reserved for the members of the division. And on Thursday, we will end around noon with some closing remarks. So the format of the talks is 35 minutes for the invited talks plus 5 minutes of discussion. The contributed talks will be 15 minutes plus 2 for questions, and then the posters as I discussed now. Okay, so we encourage you to share your camera if you are speaking, and also for questions, use the option to raise your hand so that we can have some order for the questions. And as Karen mentioned, so during the coffee breaks and also during the lunchtime, we will set up some dedicated rooms for the presenters, the talks that went right before those breaks, so that you can have more time to discuss those presentations. So we encourage you to join those dedicated discussions and have more interaction. Okay, so enjoy and engage in this meeting with all the colleagues. Thank you. So I think we can now, if you have any comments or questions about the event, you can raise your hand. If not, yes.
Before we start with the first talk, I forgot to tell you something. That we are planning to make to have the meeting photo.
Yes, a group photo, yes.
The group photo, which will be taken tomorrow, Wednesday, at the time of the first coffee break. So
here.
Yes, so if you want to be in the photo, it will be at around 11:20, more or less, tomorrow. And so set very elegant and so on, very fancy. like. And also, I will invite you to attend the assembly. I don't know the name in English. I forgot. I think it's more or less the same. But it will be tomorrow at 4 p.m. And we will have the election of the new vice president of the division. And also we will say the name of the winner of the medal of the division. So thank you very much.
Thank you, Karen. Okay, so any other comments? All right, so if no more comments on the introduction, I think we can move to the first block, which will be chaired by Dr. Ramiana. So you can now take over, Alberto.
Yes, thank you. So the first talk, we have an invited talk. This is by Dr. Tanguy Pirot. And he will tell us about when heavy ions make cosmic rays, how the QGP could solve the muon puzzle. So if you could stop sharing so that Dr. Pirot can share his screen. Thank you, Jose. I'm not so sure I see Dr.
I'm not allowed
Pirot.
yet. Hello.
Ah, hello. Very good. So
Can you hear me well?
Yes, we hear you.
Ah, now it's possible. That should be this one.
Yes. So you have 35 minutes and then 5 minutes for questions. Go ahead.
Thank you very much. First, I would like to thank the organizer for the invitation and a great privilege to start this session. So I will talk about cosmic rays and more precisely on the muon production in air showers and the so-called muon puzzle, and make a possible link with particle physics and quark-gluon plasma production. So my name is Tanguy Pirot, and I'm working at Karlsruhe Institute of Technology in Germany. So I will start with a quite general introduction because I guess not everyone is familiar with air showers and cosmic rays, and explain the so-called muon puzzle, which is actually a muon deficit in air shower simulation. I have to explain about hadronization, which is a key point in this muon production in air showers, and then make the link between this quark-gluon plasma production and air showers. So ERS stands for extensive air showers. It will be very common, so please remind it. And QGP is for quark-gluon plasma, but I guess this is more common. And for that, so we have some kind of qualitative tests with a simplified model, and I have some Monte Carlo with a modified hadronic interaction model. So the result is actually that the recent LHC data combined with also quite recent air showers meta-analysis on the muon production provide a possible explanation for the muon deficit in air shower simulation. And as you will see, this is linked to the quark-gluon plasma hadronization. So in astroparticle physics, we actually use particles to observe the universe and try to understand the different type of sources. So it's like astronomy, but we don't use light or radio waves, but real particles. So it can be either gamma rays, so very high energetic photons, which are nice because they go straight. But the problem is that they are absorbed in the interstellar medium, and we can't see very high energy gamma rays coming from far distances. Basically, it's limited to galactic sources. We could also use neutrinos, which are also going straight because they are not charged. But as you know, neutrinos have a very weak interaction cross-section. So they are very difficult to detect, but thanks to detectors like IceCube, which is a 1 kilometer cube of instrumented ice at South Pole, we could actually see such kind of astrophysical neutrinos, but the statistic is still quite low and the energy are limited. So the most common cosmic rays that we use are charged ions. But their problem here is that there is magnetic field in the galaxy and even outside the galaxy. So because they are charged particles, they are bended, and it's very difficult to see the source directly, unless you go to extremely high energy, where then the bending is, magnetic field are too weak to really bend the trajectory. But this depends on the charge and then on the mass. So what we want to measure is the source when possible. But as I said, it's only possible for very high energy and light mass. We can measure the energy spectrum that can give some information about the source mechanism. And very important is mass composition. So what type of ion do we observe? Is it something like proton, or heavier like iron? It could be actually heavier than that, like uranium, but from direct measurements at low energy, we know that there is a large drop of heavier component than iron. So typically we use proton as lower bound and iron as a higher mass. But as I said, at the same time, as I will explain you, we also test hadronic interaction in these air showers. And these two variables, the mass and the hadronic interaction, are closely bound. And one way to check whether what we see makes sense in terms of air shower simulation is that, first of all, what the reconstructed mass should be between proton and iron. And if you have different techniques to measure the mass, all the mass measured should be consistent between each other. To give you an idea of what I'm talking about in terms of energy, this is the energy spectrum of cosmic rays, charged cosmic rays. This is rescaled by the energy to the power 2.5. That make it flatter, and we see better the features or the structures. So here we start at about 10 to 12 electron volts, so 1 TeV, and this extends to 10 to 20 electron volt, which is 100 EeV. Yeah. And this is the total energy. So if you have a nucleus, for instance, this is you have to divide by 50. This is iron by 56 to get the energy per nucleus. So the equivalent energy, it's on the scale on the top. So you see that LHC is around 10 to 4 GeV in center of mass energy, which corresponds to about 10 to 17 electron volts in total energy for cosmic rays. And you see that measure 10 to 20 is actually still about 1 order of magnitude above what we will be reached at the FCC, and it's 2 order of magnitude above LHC. So you have a very high energy extrapolation of what is measured in terms of hadronic interaction at LHC and what we need to test the cosmic ray that we measure on Earth. Different colors correspond to different experiments. So the highest energy and the largest experiment is the Pierogi Observatory. We have also in Argentina, and we have a telescope array in USA, in Utah, and you see that you have some discrepancy in the energy spectrum. But they both see a cut at very high energy, which we don't know yet whether it's an effect of propagation, it's a GZK effect, or if it's the end of the spectrum from the source, like a maximum energy. So that's one thing we would like to understand. And then you have different features like the needs. So you have a break here in the spectra that we know is due to the source in the galactic cosmic rays, where you have, if you look at the composition, it's heavier and heavier. So this is the first break of acceleration of protons and up to this energy where you have iron. And then these cosmic rays are from extragalactic origin, and actually we don't know very well the mass, and that's what we want to know. So what is an air shower? In fact, it's quite simple object in principle. In the idea is you just start with the nucleus or like proton or iron or something in between, and you have interaction with air, which produce hadrons, and all these hadrons, like protons and pions, kaons, will re-interact with air, producing new hadrons, etc., etc. So you have a cascade of particles. And at some point, you will produce Pi0, which will decay into photons. This will feed the electromagnetic cascade, which will at the end be most of the particles produced, like almost 99% of the particles will be photons and positrons and electrons. But when the pions have low enough energy, they will have time to decay and then produce a muon. And this will at the end be about 0.1% of the particles are muons, but in terms of energy, it's about 10%. So this is actually enough to be measurable at ground, because muons are easy to detect and can travel far away. So you have two main kind of observables. So this is an air shower picture simulation, and you can look at from the side using the fluorescence light. And you have a typical profile like this. And this profile depends on the mass of the primary particle. So you see that if you start with iron, you have a maximum which is higher in the atmosphere than if you start with the protons, which is deeper, or even with the photons, which is even deeper. So you see that the maximum is around a few kilometers above ground. And this is usually measured in terms of vertical or slant depth, which is a quantity of matter you go through, as the particle goes through or the cascade goes through. So this is in gram per square centimeter. And this maximum is called Xmax, so the maximum of shower development. And you can measure the mean of that for over many events or showers. But you also have fluctuation. And both actually depend on the primary mass, but also on the hadronic interaction. And if you know very well the hadronic interaction, you know the mass. And if you know the mass, you could actually check the hadronic interactions. But you also have particles which reach the ground, which are photons, electrons, and muons. And this is here it's plotted the lateral distribution of these particles for different primary mass. So in the dashed line are muons, and the full lines are electromagnetic particles, here electrons. And you see they have a different slope. So if you go, this is 1 kilometer. So if you go far from the core, you actually have as many muons than electrons. And you see that the number of particles depend also on the primary mass. So that's another way to try to extract the mass of the primary particle. There is other technique like Cherenkov emissions, radio signals, that I will not talk about it. So the problem is that you have information which comes from the cascade, and you want to know what was the primary particle. And it's kind of complex problem, not by its, I mean, the principles are quite easy, but the number of particles becomes huge, like billions. And you have to really be able to trace it back. Like you have a big mess and you want to know what started that. So one of the most important ingredients are the hadronic models, which generate the hadronic interactions. And of course, we have QCD to generate these things. But unless what you do at LHC when looking at Z production or jets and so on, here we deal mostly with non-perturbative regime. So we can't compute everything from first principle. And there's a lot of phenomenology, and that's why these hadronic models are actually the main source of uncertainties of air showers. You probably know PTR or Herwick as a hadronic interaction model for high energy physics, but we use different models for air showers because they have to be able to generate events at super high energy and also in nuclear interactions. So at the end of the day, there's not many candidates. So there is DPMJet, but which is actually not used so much, but it can be used, which was updated by Anatoly Fedinich a few years ago. There is EPOS, which is used also in high energy physics and in particular in heavy ion physics. I will talk a lot about that. This is actually my model. I'm participating. Historically, one of the first one was QGLCH from Sergei Ostapchenko. It's really dedicated to cosmic ray interactions. Also Sibyl, which was first updated by Ralph Engel and lately by Felix Wien for this latest version, is also dedicated to air shower simulation. So one of the main observables, as I said, is the mean Xmax. So here I show only the mean, not the fluctuation, but you see that the different lines correspond to different models. Here for proton-induced shower, and here for iron-induced shower. So blue is for EPOS, green is for Sibyl, red is for QGLCH, and purple for DPMJet. And you see that the difference between models is about 40 grams, the difference, the total difference, so it's plus minus 20 grams around the EPOS line. And the black points here are the measurement from Pierre Auger Observatory. And the systematic error of this point is actually 15 grams. So it's less than the uncertainty due to the models we use. But in the past, you see that actually the data, if you look at all the data, you have much larger differences, but all these points are from very old experiments, and we believe that now the state-of-the-art measurement is really done by Auger, which is the largest and the more precise experiment. Okay, so if you want to do astrophysics with this kind of measurement, you arrive with this kind of plot. So you can, looking at the, if you look at EPOS, the blue line, for instance, looking at the difference between the measurements and the position between the proton and iron line, you can actually deduce, and you can actually do more a smarter way of doing that, but you can extract the mean logarithmic mass, so this mass, log of the mass, mean of the log of the mass, and this gives you, from Xmax measurement, you give this yellow band, and so the large uncertainty is due to the difference between the models. And then you want to test that against different astrophysical models, like supernova remnant and active AGN, active galactic nuclei. This will give you this kind of change in the composition, but you have also gamma ray bursts doing that, galactic difference, Emax, etc., etc. So if you want to test your astrophysical model, you have to compare to this data. And the problem of Xmax, you can measure only during moonless night, because this is light, and you measure that with PMTs and big mirrors. So you can't do that when you have during the day, or even when there is too much moon in the sky, moonlight. While if you want, you could get the mass from the number of muons at ground. This you can do 100% of the time. It's just particle detectors. But you see this greenish band is actually the uncertainty you get on the mass if you use muons. And this is again due to the models, and which have very large difference in the prediction. And even furthermore, then you see that you can have mass larger than 4, which is here corresponding to iron, so mass of 56. Basically, we see in the data mass which will be higher than iron, and this is really unlikely. And it really depends on the experiment, on the model, and so on. So here is very, very large uncertainties using muons, and this we want to solve because first of all, it means that something is wrong in the atomic interaction, and second of all, if we could solve that, you could have a lot of data on the composition, and this will help to reduce the uncertainties. So why is there so much uncertainties here? As I said, from air showers, we want, I mean, the development depends on a few parameters. You have the mass and the energy of the primary cosmic rays, that's what you want to know. And you have also the cross-section of the interactions, elasticity, multiplicity, and also so-called charge ratio, or this is also related to baryon production, which is the amount of pi0 compared to the rest of hadrons produced. So how much energy you would transfer to the electromagnetic shower. And this is very important, we'll see later, for the muon production. For instance, here in this plot, this is the number of muons. This blue line is this charge ratio. And if you just change it by few, here you reduce it by 10, 20%, or you increase it by 10, 20%, in a given model, you see that the number of muons is changed a lot. And you can go from something where your model underpredicts the simulation to something inside what is measured. And it's the same for Xmax. If you change the cross-section, you can actually change the mean Xmax predicted by for a given primary mass, the proton. You can change a lot and change and go to different measurements. So if you change the primary, you change the parameters. And so the two things are really closely related. And since we are not sure about these parameters at the energy we are talking about, because it's much higher than LHC energy, we have to find a way to actually constrain it. And one way is to measure, for instance, the mean LNA from Xmax and from the number of muons. And if both match, this means we understand the physics. If they don't match, we don't understand. And if you do that and combine all air shower experiments using a special quantity that was called Z, where you take the number of muons for one given experiment, and then you relate it to this same measurement of muons, same distance, same energy, and so on, in simulation for protons. And then you normalize by the difference between iron and proton for this given model. You get a quantity which is kind of universal that you can compare for different experiments. Then you have to take into account that the energy scale of the different experiments could be different, so you have to renormalize these energies between the experiments. I have things in the spare slide if you have questions about that. And then you have also to remove the mass dependence that you can get from this mean LNA you get from Xmax. You just have to divide by log of 56, and this will give you this Z mass. And then you arrive with a quantity delta Z, with Z minus Z mass, which should be 0 if the models, the given model you use for in this quantity is correct. And if you do that for different experiments, so here there is Amiga, which is a low energy extension of Auger for the muons, IceCube in black, Nevot-Dekor Russian experiment, Pierre Auger at high energy, so red points, Schröger experiment, Yakux, which is a very old experiment, and here these are not represented. Okay, so if you put all these experiments together with the same energy scale, you see that actually they don't lie around 0, but there is a tendency to go to have an increase with energy. And actually you can fit that. This is the different lines here, and you get a significant non-zero slope with a 8 sigma value. So it really means that the data have a much larger number of muons than what we expect from the simulation. And keep in mind that 1 corresponds to iron. So in Auger, for instance, the difference between data and simulation is as large as the difference between proton and iron. So you can't really conclude anything if you don't understand this problem. So obviously, we have problems with hadronic interaction above 10 to 16 electron volt or something like that. But this problem is not like a step, it's something increasing smoothly. And that's a very important point we discover using this method. That was not the case before. So how to relate that to any kind of physics? From a very simple model, which calls Heitler model, it's a simple cascade model, we can extract the number of muons as this simple formula. So it's just the mass A, so this is the number of nucleons in a nuclei, to some power 1 minus beta, and energy to the same power beta. And if you want to change the energy evolution of the previous plot, you have to change this beta then. And it's not a big change. It's about 4% difference in beta to reconcile the data and the simulation. But this beta is defined like that. So it's a log of the number of hadrons which will not produce pi 0, photons, so not pi 0, divided by the log of the total multiplicity. And you can write it again like this. So just 1 plus a factor, which depend on this value alpha. And alpha is simply the ratio between pi 0 and the rest on all total multiplicity. But if you want to change beta by 4%, you have to change this alpha, which is the only free parameter here, except with multiplicity, by 30%. And this is actually a lot. You could tell, okay, but if we can keep alpha constant, but change the multiplicity. But if you do that, you have the problem that you change X max, as I showed before, but this is a plot to remind you that. So here it's the mean X max and number of muons as compared to some reference. This is the OJ point. And if you start from EPOS, which is a blue line here, and you change the multiplicity by plus or minus 20%, you see that the red lines are actually on top of the blue line because you change the number of muons, but you also change X max, and both are actually going into a direction which compensate, and then you just don't change the prediction at all. While if you change alpha by plus minus 20%, you move this line a lot without changing X max, and then you could actually, this is consistent with about 30%, you will be about on the OJ point. So that's one way to go. I don't know if I have time until my normal time or if I should keep my the 10 minutes I have in advance.
You still have like 12 minutes plus 5 overtime for questions.
Okay, yeah, so I should do a little bit. So we want to change alpha, remind this by about 30% without changing the total multiplicity because we are limited by X max, which is not too bad. So how to do that? There was in the past some attempt using new physics like chiral symmetry restoration, which reduce the production of pi-0, strange fireball, which basically do the same thing. The idea is very often just to reduce the number of pi-0. And you have different approach, but all these approach were done in the past at above or at the LHC energy, because all these things is not really observed at LHC. So there is not such a strong effect. So if you don't want to change anything below LHC, you need a very strong effect at high energy. And then this is not supported by data anymore because we don't see abrupt change, which is a smooth evolution, which start actually below LHC energy. So this doesn't really work. But what we observe at LHC since a few years now, from the beginning, but now it's more and more accepted, I would say, is that maybe in light system, namely PP, but also proton-air or pion-air interaction in air showers, we observed at least modified ionization and maybe actually a production of quark-gluon plasma. A lot of things that you observe in heavy ion are seen in much lighter system like high multiplicity PP, but I will show some data. And that's very interesting for us because if you have a quark-gluon plasma, this alpha, this number of pi-0 divided by total multiplicity, is reduced too, because you get relatively less pi-0 compared to the baryons, strangeness, etc., which are increased in the quark-gluon plasma hadronization. And so this, since alpha depends on the hadronization, this could be one way to change alpha. So what is done now in the hadronic models? There is two extreme cases which are used. There is either string fragmentation, so this is based on E plus E minus interaction, and then fragmentation of your QQ bar pair, which is produced from the photon or Z0 decay. And this is a well understood process with a color field, and you produce a chain of particles, and this works very well in dilute systems and in low energy PP or in electron positron. And this is actually what is used in most of the model. But when you go to dense systems, so heavy ion collision, we know that this doesn't work, and its collective hadronization is used, so a statistical model where you have a phase we don't know very well, and then the quark-gluon plasma, hadron gas, and then some non-equilibrium state. So the problem is that in our case, we are neither really in dilute system nor in a dense system. So in the current models, as I said, we mostly, for theoretical and practical reasons, string fragmentation is used. Because we thought that light systems were not dense. That works quite well at SPS, so low energy at CERN. But in fact, if you look carefully at data, there is some tension at weak. At Fermilab, the data were already not so well described. And if you look at the details of LHC data, this pure string fragmentation doesn't really work. So you need to change it compared to E plus and minus. So there are different schemes like color connection or string junction, string percolation, depending on the model. But all these things you need to tune to data, and the more data you have, the more parameter you need and you have to change. And this statistical model for heavy ion works very well with hydrodynamical evolution to do coagulant plasma ionization for lead-lead collision. You have flows, strangeness, everything works very well. But this was never used for air shower because people thought with oxygen or air and proton or pion, this is not dense enough. But to actually really reproduce the data we observe at LHC, there was a third way, which is the core corona approach, where you can use strings to actually generate pseudo particles or fragments, which helps you to compute some energy density in a heavy ion collision, like this, for instance. And then you can see regions where you have high energy densities, and you can call core. And then this core you can hadronize using a coagulant plasma approach. And you have around it, you have low density particle, low particle density, and this is called corona, where actually you can use string fragmentation as observed in a plus and minus collision. So you could actually mix both approach. This is what is done in EPOS, for instance. And if you compare this to the more recent data from ADIS, for instance, where you mix proton-proton, proton-lead, and lead-lead data. So this is a particle multiplicity amide rapidity. And you see that you plot the ratio of particle to pions. So this is K short over pions, lambda over pions, cascade over pions, and omega over pions. And if you look at the multi-bion, multi-strange bions like omegas, you see that you have a smooth evolution from PP to P-lead to lead-lead, where you have some kind of saturation. This saturation reaches what you get from a coagulant plasma production, and you start this red line here is PTIA, so this is pure string fragmentation, and you see that you are even at the very beginning, you are already largely above. And then you will go even further. So you have different approach, and in EPOS LHC, so the old model, we had this trend, but qualitatively, but quantitatively, it was actually starting too late and going too far. So, and in terms of PP or light system, the later you start, the more rare it is. And this could be actually a problem for air shower. And with a newer version of EPOS, here where you really do this core corona approach properly, you see that actually you can reproduce this evolution. So this data and this data are the same. You go corona to core, and just by changing the relative fraction between core and corona, you can actually reproduce this particle ratio. So that's the idea we want to apply for air shower simulation. We can use a model called CONNEX, which is air shower simulation code based on cascade equation, where you can artificially change the particle ratio. And the idea is actually to change, as function of energy, the ratio between the particles, going from what the model gives you at the beginning, so corona-like hadronization, to the core-like hadronization, and we fix that using lead-lead data. So you get particle ratio like pions, etc., protons, as observed in lead-lead. And you can change it as function of energy. So your number of particles is simply the fraction of core times the number of particles in a core with 1 minus core fraction to the corona type of particles. And you can change this W core as function of energy. So this gives you these different lines. So as you start from 100 GeV, you go up to 10 to 19 or 10 to 10 GeV. And you can decide whether you have only 25% or 50, 75, or 100% of particle coming from the core at the highest energy. Or you can even reach 100% earlier, or even be 100% all the time. So from 100 to 10 to 10 GeV. This is, of course, excluded by the data, but in fact, if you look at LHC data, this kind of value here is, in fact, possible. Actually, would be here. About 50% of core particles is what would explain best LHC data. So if you do that on the models I talk about, like this EPOS LHC, for instance, you have this alpha I want to modify. This can be written instead of number of particles just by energy density in terms of pseudo rapidity, and we can call this ratio R as function of eta, so pseudo rapidity. And you can plot that as function of energy with R, either for eta equals 0, mid rapidity, or forward, which is about 10% of the projectile energy. So the black line is the default value of the model. And if you apply this, this line here, 100% at 10 to 19, you get this blue line. And if you use this evolution, you get this dotted line. This is the R value for the coagulant plasma, and this is the corona case. So you go from corona to core, and depending on your change, you see an evolution. And you see that it's about 17% change at mid rapidity or 16% at the forward. So it's not yet the 30% we would like to see, but maybe that's already good enough. If you use QGIS, another model, then you actually the change is more like 20% in both cases, mid rapidity or forward. And for CBIL, it's also about 16%. And if you do that in this kind of representation, so you have Xmax again, and here's the number of muons. This is a measurement from G. And for QGIS, this is the original model. And then this is the different lines I showed before, 25% of core at the highest energy, which is the energy of the measurement here. 50%, 75%, 100%, and these are more extreme cases. But you see that actually with something realistic, which is about here, we are 1 sigma off from the data, which is already much better than before. With EPOS LHC, we are actually less than 1 sigma. And if you use CBIL, which has a higher mass, so deeper Xmax, so all these lines are shifted to the right. And you see that, in fact, you don't need much. And the uncertainty here is driven by the energy scale of Auger, so this can easily be anywhere in between. So this is still not good enough, but it's actually going close to what we need. And if you put that in this representation, you see that, in fact, you indeed change the slope, maybe not as much as we would like, but it's still compatible with data within 1 sigma now for both models.
Okay, now it's our time.
Yeah, okay, so I can skip that because it's just the same, but in practice, you're changing EPOS. So nothing, just the same conclusion that in practice, you can actually do that in a real Monte Carlo and you get the same kind of results. So it's very encouraging. So just a summary. So the WIS group, which did this meta-analysis, was very important to understand that the so-called muon puzzle, or the increase of or the deficit of muons in data, in simulation, sorry, compared to data, is not a sudden increase, but something smooth, starting about 10 to 16 electron volts. So this ruled out some kind of explanation. It cannot be something like a new physics which appears above LHC only. More data are more analysis are needed with the Nightingale, muon energy, etc. This is ongoing analysis. So to explain that, most natural is to change this electromagnetic to hadronic energy ratio. The rest are limited by Xmax, so you can't really change multiplicity or inelasticity. And one of the best solutions for that is actually to take what LHC teach us recently, that actually we observe coagulant plasma like hadronization in light system, and that's why we would need proton oxygen data to confirm that and to see how much this how strong is this effect in proton oxygen, for instance. So it goes in the right direction. It might be enough within the uncertainties, but with more precise data, we would see whether we need even more, also some additional physics, maybe at high energy or not. But I'm not sure. And of course, not everything that is measured at LHC and CERN now is in the model. So further improvement of the models will also contribute to reduce these uncertainties. Thank you.
Thank you, Tianguy. We can have a couple of questions. You can try raising your hand with going to reactions, or you can try asking the question. Well, I can make one question while. So there is some comparison. You mentioned in your conclusion slide that there is still missing comparisons with, for example, data at different zenith angles and all that, but there's plenty of data around. So I guess there is room for making a deeper comparison with the data still, right?
Yes, yes. So what I mean is that, in fact, we mixed, so for the width group, so these all are the data which are used. And here you see the zenith angle, this is the distance, and this is the energy threshold of the muons. So you see there is actually everything is covered kind of. So like IceCube is for vertical showers only, while OG is for inclined showers. And some other experiments are in between, and so on and so on. So what I meant is that we mixed everything all together. And what we are doing now is actually to try to look at different direction for fixed energy, or for, to see whether there is another dependence in zenith angle or in distance, or some, which would be second order effect, but which might be important to understand. So data are there. What we need to do is to analyze them in a different way.
More systematically, let's say.
Yes, yeah. But it's ongoing, yeah. Probably show that IC, next ICRC.
Thanks, thank you. So any other question for Dr. Pirot? Nick Mulder has one.
Yeah, so I don't know if you can hear or see me. I guess so.
Yeah.
Yeah. So I was wondering, because so I'm from LHCb, right? And from our side, we also do studies of hadronization, and we see effects in strange quarks. So I guess my first question is more in general, do you also expect that you can get something from charm hadrons and or from beauty hadrons?
Yes, so here I talk about low energy muons, so about 1 to 10 GeV at ground from air showers. So these are produced by standard particles and strange, and so kaons and pions. Charm, do I have? Not sure. So charm particles are also very important, but not for this problem, but for the very high energetic muons, which are above 100 GeV, which you can measure in IceCube, for instance. So IceCube is this experiment at South Pole. So where you have as I said, 1 kilometer cube of ice with PMTs inside, and this 1 kilometer is about, I think, 1.5 or 2 kilometers deep underground, below the ice, below the surface. It's all ice, but it's below the surface. And this means only very high energetic particles can go through, and muons, high energetic muons, can reach the detector. And these muons are actually generated by charm. And for them, for charm particles, for them, this is the background of also high energetic neutrinos. So understanding the charm production is very important to actually get a correct spectrum of neutrinos. So this is another large uncertainties where LHCb is important to measure forward this charm production. And beauty, but beauty is even more rare than charm. So That's,
I can imagine for the showers, indeed, it's less important in that sense.
Not considered yet, I have to admit.
Yeah.
Maybe we neglect something here, but yeah, in principle not.
Yeah. But it was nice to see this core corona model. Let's say that seems to explain some of these things nicely. So we should also look in LHCb how that compares to some of these PVA color reconnection models. That's actually a very important point. Is that so on this plot here, what matters for air showers is actually what is forward, not at mid rapidity. And LHCb, which is here, is actually on the edge of this growing thing. So if LHCb could actually measure the same type of strangeness enhancement we see at mid rapidity, that would be very helpful to understand if we actually have this kind of effect in the forward hemisphere, which is the largest hypothesis in this analysis we did, is to say, okay, we have the same forward than we see at mid rapidity, but this is not measured yet. So if LHCb could actually already see such kind of effects or increase of strangeness as function of multiplicity, that would be very helpful. Yeah. Okay, that's interesting to know. Thanks. Yeah.
Thank you. So we have two questions, one by Wolfgang Hittenholz and one by Juan Carlos, who mentioned in the chat. So first, Wolfgang, please.
Yes, thank you. I wanted to ask, your model is in agreement with the crossover temperature, which is usually assumed for the quark-gluon plasma, about 155 MeV. And what is the crucial property of the quark-gluon plasma that could possibly solve this muon puzzle?
So here we, so in this approach, but also in EPOS, like here, so this is really lead data. So we use the equation of state of quark-gluon plasma on the lattice to do the simulation, and then we have a freeze-out temperature, which is kind of standard values. Yeah? So this is what you extract from any statistical model. So, and we stick to that in this approach. So maybe because here we are some models, some authors claim that if you are very boosted in your projectile, maybe you could have higher baryonic density, and then this would change the hadronization parameters, and then having even more strangeness production and so on. But this becomes more speculative. Here we were kind of conservative, using what is observed at LHC and this temperature, and this doesn't change with energy or whatever. So this is a kind of a standard value which corresponds to this saturation here. I don't know if it answers your question, but
it's okay.
Yeah. Thank you, Juan Carlos.
Yeah, there was a part on for the formation time. This is not. This is just a parameter, and this is just like 1 Fermi over C or something like that. We don't know what happened, if there is stabilization or not. We just assume it. Yeah. This cannot be done in the model.
Okay, thank you, Juan Carlos.
Thank you very much. Hi, Tanji. Very nice talk. One question. Well, I can see that you can describe the bulk of the data regarding the total number of muons. For example, some details about which are sensitive, for example, to the spectrum of muons, like the muon attenuation length or the dependence of the muon with the zenith angle, or for example, the lateral distribution of the muons. Have you tried to see if there is some also some information about that?
Yes, so it's a very good question. So about the lateral distribution, for what we saw using Connex, but this is not a full model, there was no big change in the lateral distribution. Using real Monte Carlo, I didn't look at the lateral distribution, so I don't know, but this is something we have to do, of course. Concerning the muon energy spectra, this is quite interesting. You see, so EPOS QGP is this modified EPOS, like trying to reproduce, to have more quark-gluon plasma-like hadronization at forward and also at earlier in terms of energy. And the blue line is EPOS divided by QGZ for the energy spectra of the muons. So this is the energy of the muons here. And the purple line is this modified EPOS. And you see that, very interestingly, it increases the number of muons everywhere, not only at high energy, like in the case of EPOS LHD, but starting above 100 GeV, because it has more strangeness. So it has more kaons, and then it has higher critical energy. So, and this would probably help for the muon attenuation length, because you get, in average, larger energy per muon. But I didn't look directly at that, but it really goes into the right direction, I would say.
Okay.
Okay, thank you.
Thank you very much. Thank you, Tanguy, for your talk. And I think we have to proceed to the next one, which is, in fact, by
Thanks,
Juan Carlos Arteaga from the Universidad de Michoacán.
Goodbye.
And Juan Carlos is going to talk us about the investigation of the proton plus helium cosmic ray spectrum in the 10 TeV to 126 TeV energy range with the Hawk Observatory. So go ahead, Juan Carlos, you have.
Okay, thank you very much. Thank you. It's a pleasure to be with you to talk about these results about the Hawk measurement, cosmic ray composition. So let me start by giving a little bit of the motivation of this work. So as you know, cosmic rays are also a hot topic in astroparticle physics. This radiation is one of the most energetic and also enigmatic form of radiation from outer space. Here you can see the corresponding energy spectrum, which can extend from 100 MeV up to 10 to the 20 electron volts. They are mostly composed by atomic nuclei. Protons and also helium nuclei are the most abundant particles there. We have also electrons and also traces of antiparticles. The energy range goes from in this energy interval. Also, you can see that the spectrums follows roughly a power law of this form. There are some features in the energy spectrum, and as you can see over here, and for example, the knee and also the other structures. And we know also that the origin can be found, for example, in cataclysmic galactic and also extragalactic events in the universe. There are a lot of questions, unknown questions, for example, regarding the origin of the features of the spectrum, these ones over here, the sources, the propagation, and the acceleration mechanism, whose answers are still unknown. In order to give some hints about the possible answers to these questions, we need data, for example, about the spectrum of the cosmic rays, the composition, the arrival times, and also multi-messenger and multi-wavelength observations. From the energy spectrum, one of the regions which has been not very well explored is the one corresponding to 10 TeVs up to 1 PeVs, which we can see in this plot on the left-hand side. So this is the region at the limit between direct and also indirect detection. That's why it has been historically a little bit difficult to study. Because of that, we have not enough data to make basically studies about the composition and also the shape of the spectrum, which is sensitive to the different mechanisms and also the physics of the cosmic rays. But now, due to different progress in particle physics and also in the detection of particles and also in air showers, in detection of air showers, so we have just started for a detailed exploration of this energy range. So one of the things that has came up recently, it's regarding the composition in the light component of cosmic rays. So early measurements with at, for example, 0.2 and also CRIM 2.3 and also nucleon have hinted the existence of a break in the energy spectrum of the light component, that is proton plus helium nucleon, at around 10 TeVs approximately. Unfortunately, due to the lack of statistics, as you can see over here, there has been not really a discovery or really a confirmation about this structure in this energy range. So the idea is to try to study this energy interval by using the Hawk Gamma Ray Observatory. The Hawk is basically an air shower detector. It can detect gamma and also cosmic rays by using this technique. It's basically based on a ground Cherenkov technique, and it basically detects air showers coming from these primary particles in the energy range from 100 TeVs up to 100 TeVs. You can see, for example, measurement of the skies in the gamma ray regime. And on the other hand, the detector is located at very high altitude, which basically allows the detector to make this kind of studies in this very low energy regime. Remember that the atmosphere absorbs low energy air showers, so the highest the altitude, the better the detection of these low energy particles. So the Hawk detector is located at the Sierra Negra volcano in Puebla, Mexico, here in this latitude and longitude, and it's located at an altitude of 4,100 meters above sea level. And the setup is basically seen in this picture on the right-hand side. It covers around 22,000 square meters of surface and is composed of an array of 300 densely packed water Cherenkov detectors. Each of these detectors is composed by a tank of 2,000 liters of water plus four multipliers, which can be seen at the top of each detector. So what we measure from the air shower is basically the arrival time of the shower to the detectors, and also the total charge deposited in each of the PMTs from which we are working. From the heat times of the PMTs and also the deposited charge and also the number of PMTs with signal, we are able to find the core location, the arrival direction, the fraction of heat PMTs, and also the lateral charge profile. From here, we can reconstruct several properties of the air shower. For example, we can study the lateral shower age, and also from the total amplitude of the signals, we can find the primary energy. For one of the parameters which is very sensitive to the composition is the lateral shower age. This shower age parameter can be found by using a fit of the charge of the lateral charge as a function of the radial distance to the shower core in the corresponding shower plane. So basically, we applied a fit like this with this radial formula, and here you can see this parameter which controls the corresponding shape of this distribution. From the fit, you obtain this quantity and also the amplitude of the signal. And you use this quantity, the shower age, in order to study the composition. The flatter the distribution, it means that it's related with a heavy cosmic ray. And the more steeper the distribution is related with a light primary. And you can also use this distribution in order to make fits with, for example, templates obtained directly from the Monte Carlos, corresponding to protons with different energies, and from a corresponding maximum likelihood fit, you can find, according to the measurements, the corresponding energy from this air shower event, assuming that they are composed by protons. Now, for this study, and also in general for the study of cosmic rays, you need Monte Carlo simulations. We have used Corsica and acidonic interaction models, low and also high energies. We have used Fluka and also QGG204. We have also used POSLAC in order to study the effect of the high energy atom interaction model in the measurements. And we have applied also a full simulation of the detector response by using GAN4. We have used produced data with zenith angles below 70 degrees, and we have thrown these events uniformly, homogeneously inside an area of 3% to the 6 square meters. That is a radius of approximately 1 kilometer from the center of the array. As a primary nuclide, we have used 8 primary nuclei: protons, helium, carbon, also oxygen, neon, magnesium, silicon, and iron nuclide in this energy range. And all of them, this spectra were produced with a ET to the -2 shape, but the data had been reweighted in order to try to reproduce the corresponding spectra for the different primaries that were measured directly in experiment like MS2, the CRIM2, 3, and also Pamela, as you can see from these plots on the right-hand side, where you can see the corresponding fits. Now, we have used also different composition models in order to study the sensitivity of this analysis to the different hypotheses on the composition. For example, we have used models inspired in data, real data, from direct experiment like ATIC, JC, and MOVIE, and also from other models, for example, the polygon ARTO. So here you can see in blue the predictions for the light component, and also for the heavy component, you can see the predictions in red, and the relative composition in these models of the light to the heavy component. You can see the behavior for each of these models on the right-hand side as a function of the logarithm of the primary energy. Now, we need, for this kind of analysis, to apply different selection curves in order to reduce the effect of systematic effects on our analysis. So we have concentrated at the moment with zenith angles below 17 degrees approximately, only vertical data. We have selected only data which were successfully reconstructed, in which we have obtained the core and also the rival direction. Also earth showers which have activated at least 40 PMTs with a radius of 40 meters from the core. Mainly we have used data on array data, and also earth showers which have a multiplicity threshold of around at least 75 PMTs. Also, we have used a fraction heat, which is defined in this way. That is the number of heat PMTs divided by the number of available channels, greater than or equal 0.2. And we have worked in the energy range from 10 to the 3.5 up to 10 to the 5.5. So by using these selection codes and using the corresponding Monte Carlo data, these are the corresponding expected performance of the detector. Here you can see the behavior of the resolution of the logarithm of the primary energy as a function of the primary energy, and you can see also the corresponding bias, which is decreasing with the energy. You can see also the resolution in the arrival direction, which is smaller than 0.45 degrees, and here you can see for also the resolution in the core position, which is better than 15 meters approximately, which is good in order to do this kind of studies. So the idea of the analysis. Yes, thank you. The idea of this analysis is basically to make a selection on the to obtain a subsample using a cut on the shower edge. The subsample must be rich in protons and also a helium nuclei. So for that, we use a Monte Carlo simulations from QGA204 for different primary nuclei. So here you can see the shower edge, which is sensitive to the composition as a function of the primary energy. So we apply a cut to make this selection, a cut between helium and also the prediction for carbon. So everything which falls below this line will be considered as a like component. So we select this like component, so you can see the corresponding abundance in the subsample of protons and helium, which is pretty big, around 80%, and the contamination of the heavy component, which is below 18% approximately. Now, after the selection, so you can see that you can apply directly to the experimental data. Here we have used data for corresponding to 3.7 years approximately, which spans this period of time from June 2015 up to June 2019. And after applying these quality cuts and also using this age cut selection, we get around 10 per 10 to the 9 air showers approximately. Now, after using this cut, anti-selection, you need to correct for migration effects. In order for the correction, we have used an Bayesian unfolding algorithm, which will be explained in the next talk by Jorge. So the idea is to make the correction by using this formula and also an iterative procedure based also on the Bayesian approximation. So for that, you need as an input the measured data and also a response matrix, which is calculated by using these QGS204 simulations. So the stooping criterion is basically the minimum of the weighted mean square error, which is the sum in quadrature of the statistical and also the systematic errors, as you can see from this relation. Now, after that, you need to correct for contamination of the heavy elements. This factor of correction is calculated by using also simulations. And after that, you calculate the corresponding effective area as a function of the primary energy. Once that you have all of these elements, you use this formula in order to calculate the corresponding flux associated with the proton plus helium nuclei, which can be seen multiply it by a factor of the energy to the 2.6 approximately. So here what you can see is the measured data from Hawk, and also as an error band, you can see the systematic uncertainties and the statistical uncertainties. You can see them in error bars. So you can see one of the things that the result is a break in the spectrum around 30 dBs approximately. This is important because it has been not seen before in a previous measurement. It was hinted by previous experiment, as I have explained, for example, CREAM. This structure seems to imply different things. For example, one of the things is for it could be a new cosmic ray accelerators besides PeV supernova remnants, but with lower energy. Maybe it could be associated with a local cosmic ray source at distances of order 100 parsecs, for example, or maybe some modifications to a standard mechanism of cosmic ray acceleration in astrophysical shocks. We don't know exactly what it could be. So here you can see that we have considered different statistical and systematic uncertainties at an energy of approximately 10 to the 4.5 GeVs approximately. We have an error between 10% and also minus 9% approximately, but it's increasing as you go to very high energies. Now we have used a study also the significance of this structure by comparing different hypotheses, one corresponding to a single power law and the other one to a broken power law. So we have used a study based on a statistic which is employed the minimum of the chi-square. So we have used two fits by using this power law fit and also this broken power law fit, and we have used this test statistic. And from the result of this statistic, we found a p-value lower or equal 4 × 10⁻⁵, which implied that this structure can be seen with a significance of 4 sigma approximately. So this deviation, this is a deviation of 4 sigma from this scenario, which implied a single power law. So it means that it is unlikely that the data is described by this single power law approximation. So the results for the broken power law fit is like this, and you can see that the spectrum seems to change of the spectral index are around 30 dBs approximately.
Over time now.
Yes. So just to end, so here you can see the comparison with different measurements, direct measurement from ATIC, CREAM, and nuclear. It seems that it's confirmed basically this structure that it was hinted before by this another experiment, but it doesn't support the previous observation by the direct experiment, Argo YBG, which implied that the spectrum was following a single power law formula expression, as you can see from this relation. So basically that is all. So we have performed a first analysis of cosmic ray composition with Hawk, which has allowed to reconstruct the spectrum for the light component of cosmic rays, that is proton plus helium, in this energy range. We have found that the result is in agreement with data from Nucleon and ASTOP, but a little bit above estimation from this and other experiments. The Hawk data seems to observe and structure a change of the spectrum around 30 dBs. And this study is important because it demonstrates that the high altitude Warren Cherenkov observatories like Hawk can be also used to study the composition of cosmic rays at energies as low as 10 dBs. So thank you very much. And if you have some questions, please, or comments.
Yeah, we have time for like one question. Or I can make one comment, which is in your sources, your potential sources for the break. You mentioned the supernovas, PeV supernovas there, yeah. So one cosmic ray accelerator that is emerging is a pulsar wind nebula and the TV halo. So that could be an analysis, well, something to provide to the theoreticians to work on.
Yes, what the result seems to imply is that there are new populations of cosmic ray accelerators with lower energy. We are talking about energies of between 10 TVs and 100 TVs. That is, it could imply maybe a new kind of population. What maybe could be this kind of new objects or something else. We don't know exactly, but that would be also an interesting possibility.
Okay, thank you very much. Thanks, Juan Carlos, for this nice talk. And the next speaker, I hope he's here around, Jorge Morales Soto. He's going to tell us about the all-particle cosmic ray energy spectrum as measured by the Hawk Observatory. So Jorge, yes, you are here.
Hi. I'm going to share my screen.
Please do.
Yeah. So, can you see it?
Yes, and you have 15 minutes.
Okay, thank you very much. Hello, everyone. Well, my name is Jorge Antonio Morales Soto. I'm a PhD student from the Instituto de Física y Matemáticas de la Universidad Michoacana. My advisor is Dr. Juan Carlos Arteaga. And today I'm going to talk about the all-particle cosmic ray energy spectrum measured with Hawk. And well, the outline of the presentation is going to be a little introduction and the motivation of this work. I'm going to give a brief introduction to the Hawk Observatory, and then I'm going to move on to the analysis and the results, and finally the conclusions. So as for the introduction, well, Juan Carlos already mentioned something about the energy spectrum. So we know that the energy spectrum contains key information that can help to unravel some of the mysteries behind the origin and propagation of the cosmic rays. And one of the regions that has been less explored is the region between 1 TeV and 1 PeV. And because it is between the region from the limits of the direct measurements and the indirect measurements, as you can see in this graph over here. So we have this region of interest. And as Juan Carlos mentioned, this is due to some of the difficulties of the techniques and the technology used in these type of detectors. And of course, naturally, over the years, the technology has evolved, and there is a new generation of detectors that is contributing to this region. One of them is the Hawk Observatory. And previously, the Hawk collaboration back in 2017 published their first result about the measurement of the all-particle energy spectrum from 10 to 500 TeVs with 8 months of data. And here we can see the results. They go up to 500 TeVs. It is compared to other results from other experiments. For example, we have ATIC in here, Nucleon, which is this red process, and other indirect experiments such as iStock, for example. One of our main goals is to extend this study up to 1 PeV using Hawk and providing an increase in the statistics. So our mission is to extend up to here, so we can contribute to this region of interest. And now moving to the Hawk Observatory. Juan Carlos already gave a nice introduction to the observatory. I'm going to be brief. One of the main scientific objectives of Hawk is to extend the measurements of the gamma rays up to 100 TeVs, and also to study cosmic rays between 100 GeVs and 1 PeV. It is located between the Pico de Orizaba and the Sierra Negro volcanoes at an altitude of 4,100 meters above sea level. It has an area of 22,000 square meters, of which it has 62% of physical coverage. It has 300 water Cherenkov detectors and 1,200 photomultipliers. In here you can see a picture of the site. At the background you see the Pico de Orizaba, and these are the Cherenkov detectors. You can see that sometimes it gets snowy. And for those of you who have a T-Rex at home, you can easily imagine the height of these tags. And as for the simulations, the showers at Hawk are simulated with Corsica. Within Corsica, there are 2 hadronic interaction models that are employed. Fluka for low energies below 80 GeVs, and the hadronic interaction model QGS-204 for energies greater or equal than 80 GeVs. The interactions with the secondary particles on Hawk are simulated with Jan4. And we have 8 species that are generated in the simulations, from hydrogen to iron. and the spectra is weighted according to the fits of CREAM, Pamela, and AMS. Here you can see how these fits are being done to adjust the spectra. They're generated between energies from 5 GeVs to 3 PeVs, are homogeneously distributed over a circular area of 1 kilometer of radius, and they describe anisotropic flux. And for the selection of data, we use some quality cuts to diminish the systematic effects in the core position and in the variable direction. This is that we select events that have an variable direction less than 35 degrees. We also select events that activated at least 60 channels in a radius of 40 meters from the shower core that fell inside of areas, registered signal in at least 75 channels from a total of 1,200, and activated more than the 30% of the available channels. And once we have the Monte Carlo data, we're going to study the energy, the angular, and the position bias. So we can characterize the data that we are using. In the left side, we have the energy bias. We have in the middle, the angular bias. And in the right side, we have the core position bias. And for an energy of 10 to the power of 4 GeVs, we have that the angular bias is equal to 0.52 degrees. For the core position bias at an energy of 10 to the power of 4 GeVs, we have that it is equal to 14.5 meters. And finally, the energy bias at the same energy is equal to 36%. And moving to the analysis the results, we use, for this study, we took a subsample of events that were taken from January 1st of 2018 to December 31st of 2019. And we only selected events with energies between 10 to the power of 3.5 to 10 to the power of 6 GeVs. The total time of the sample is 703 days. This is the number of events that we have before the quality cuts that I just described. And this is the number of events that remain after we apply the quality cuts to this subsample. And in here we have the measured energy distribution after the quality cuts, which I'm going to call the raw energy distribution. Why I call it this way? Because it is only applied the quality cuts. We haven't applied yet a correction for migration effects. Some effects due to the detector or the efficiency of the detector. We're going to use this distribution to reconstruct the energy spectrum, but we need to correct this for the things that you said. So we can obtain the true distribution of these energy events. So how can we do this? Okay, so we want from the raw distribution, we want to get the true distribution of energy. We're going to use an iterative procedure called the Bayesian folding, which is going to help us correct for efficiency, migration effects, and effects from the detector. So the first thing that we're going to use is the response matrix, which is calculated from Monte Carlo data. Once we have this, we plug it into the Bayes formula. And one thing that we also need is the prior information in the first step of the distribution of under study. If we don't have any information of the distribution under study, we can use a uniform distribution and plug it in here. And once we have everything in the Bayes formula, we can proceed to get a first approximation of the true event distribution. And from the true event distribution, we can get a first guess of the final probability. And as I mentioned, this is an iterative procedure. So once we have the final probability, we can take it and plug it back into the Bayes formula. And we can go again. So from Bayes formula, we get a guess from the true event distribution. And then again, we can get another guess from the final probability. And we go back to the Bayes formula and so on. But Obviously, we cannot do this to infinity. We need to stop at some point. So that's why we need a stopping criteria to select the number of iterations. This can be set by the user. In our case, we use the weighted mean square error, which is the square sum of the statistical uncertainties and the systematic biases. And we're going to use the minimum to stop the iteration depth. Once we found this minimum in the iterations, we set it as our stopping criteria for the iteration depth, and therefore we can select how many iterations we want for this procedure. 5 minutes. Okay, thanks. Now we have we need inputs from the Monte Carlo data, and here we have the response matrix. In the y-axis we have the reconstructed energy, and here we have the true energy. This tells us, for example, what is the probability of an event with an energy of 10 to the power of 5 GeVs, the probabilities of with what energy it is going to be reconstructed. That's why we have the probability in the z-axis from 0 to 1. We can see that Fox response becomes linear for energies higher than 10 to the power of 4 GeVs. And also we need the effective area for the reconstruction of the energy spectrum. We can see the maximum trigger and the reconstruction of efficiency for Hawk is at energies higher than 10 to the power of 4 GeVs. And this is the formula that we use to estimate this effective area. Once we have all, we have now the true energy distribution from the unfolding, we have the effective area, we can proceed to reconstruct the energy spectrum. In here, we have the all-particle cosmic ray energy spectrum measured by Hawk. These are the results from this work in the black dots, and the squares correspond to the study made by the Hawk collaboration in 2017. We have the statistical uncertainties for both of the results, but the markers are bigger than the statistical uncertainties. That's why they can be seen here. This gray band corresponds to the systematic uncertainties for these results, for the results from this work. And we have the contributions for this band. We have the PMT efficiency, the PMT late light, the PMT threshold, the PMT charge, the zenith angle, the unfolding technique, the seed and the smoothing in the unfolding, the effective area, bin size, and composition model. Also, once we got the result, we applied a fit to the spectrum using a broken power law, using a K-square minimization procedure, and we get these results from the fit. We have that the spectral indexes are gamma 1 is equal to -2.5 and gamma 2 is equal to -2.7. And the energy break at the knee is equal to 50 TeV. From here, we can see that the break in the spectrum is shifted to large energies in comparison with the results from Hawk in 2017, which it was reported to be at 45.7 TeVs. The uncertainties on the flux, we have in here the total systematic and statistical uncertainties. The statistical error to an energy of 10 to the power 6 GeVs is between 2.8% and -1.8%, and the systematic relative error to an energy of 1 PeV is between 8.7% and -13%. And we have here the individual contributions to the systematic total uncertainty. In here we have the unfolding, the seed, the smoothing in the unfolding procedure, and the bin size, shimming quadrature, added in quadrature in here. We also have the composition model in here. And finally, the effective area in this side. And in the right side, we have the contribution due to the PMT efficiency, the PMT threshold, the charge, and the late light, added in quadrature as well in here, and the zenith angle. And we can see that the systematics are being dominated by the PMT efficiency, the zenith angle, and the composition model. And finally, we have the comparison of the results obtained in this work for the all-particle cosmic ray general spectrum compared with the results from direct and indirect cosmic ray experiments. We see here, these are our results. We can see that there is in good agreement with the results published by the Nucleon collaboration. And also we see that there is, if we could extend our results. We could see that they would be in agreement with, it tends to follow the results from the iStop research. And from conclusions, we have extended the measurements of the energy spectrum of cosmic rays with HUC up to 1 PeV using data with high statistics. In addition to the measurements of nucleon, the results of this study offer a first bridge between direct and indirect measurements of cosmic ray energy spectrum between 10 TeVs and 1 PeV. We studied several sources of systematic errors. We found that they are dominated by PMT efficiency, the zenith angle, and the composition model. And at an energy of 1 PeV, the statistical error on the flux is between 2.8% and minus 1.8%, while the corresponding systematic error is between 8.7% and minus 13%. Also, our results from this work are in good agreement with the results published by the HUC collaboration in 2017 and the results from Nucleon. And also, as a final step for this work, we are working in the systematic error on the flux due to the hadronic interaction model by studying using the EPOS LHC model. So thanks. If you have questions, comments.
Thank you. I believe Wolfgang has a question.
Yes, just if you could be a bit more specific, what does this broken power law mean? What is the exact function?
The exact what?
Yeah, the exact function that you call a broken power law. What is it?
Oh, we're using this function over here to just, it was a quick test to see the position of the break. So we could compare it with the previous report from the collaboration in 2017. So we use this function in here for that part of the study.
Okay, okay, thank you.
Yeah.
Any other question?
And just as to complement this, we're currently working on a test of statistics to see if it is best described by a broken power law or a double power law or a simple power law. But this is currently going under study.
Okay, very good. Thank you. Okay, we thank Jorge Morales, and we move to the next speaker. To close the session is Carlos Rodriguez Benitez. He's going to tell us about universe and holography.
Yes. ¿Sí se logra ver mi pantalla?
Ya se ve.
Ya, sí, ya se ve. Bueno, en este caso...
Se ve un poquito cortada por abajo.
Oh. A ver, voy a poner pantalla completa, voy a poner.
Sí, ahí está mejor.
Sí, ahí está mejor. Ok, bueno, buen día con todos, agradecer por la atención y además de ello poder presentar aquí este trabajo. Es un trabajo de investigación que finalmente ha tenido, bueno, bastante acogida por parte nuestra. Somos un grupo de investigación de física teórica, como pueden notar aquí. Bueno, quien les habla es Carlos Rodríguez Benítez, también está integrado en el grupo el doctor Antonio Rivas Plata, el maestro Freddy Medina. Bueno, anteriormente también se encontraba el doctor Marcial Vázquez, ahora se encuentra en otra universidad. Y bueno, finalmente también está, y no menos importante, el doctor Mauricio Cataldo, que es uno de los principales investigadores en esta línea, ¿no? Este trabajo se pudo hacer gracias a un financiamiento de un proyecto de investigación y además de ello también se pudo hacer gracias a un trabajo entre universidades peruanas y chilenas, ¿no? Bueno, el trabajo que voy a presentar ahora tiene un lineamiento de esta forma. Primero voy a hacer una breve introducción orientada fundamentalmente a que nosotros podamos entender, bueno, todos en general se puedan enfocar un poquito en el trabajo que hemos hecho. En una segunda parte vamos a plantear cuál es el momento en que insertamos la parte holográfica dentro de este modelo. Y por tercer momento vamos a estudiar los modelos de interacción en donde se presentan múltiples universos. Bueno, en realidad la posibilidad es de muchas maneras, solo que nosotros nos hemos concentrado en estudiar algunos que son los más viables y evidentemente más se acogen al background cósmico, ¿no? O cosmológico que tenemos ahorita de la data. Bueno, finalmente algunas conclusiones y algunos trabajos que hemos podido presentar, y si alguno de ustedes también desea indagar un poco más, podría ingresar a ello, ¿no? Parto mostrando cuál es el componente actual del universo. Bueno, en realidad no ha cambiado mucho del año 2010, por ahí ya se viene proponiendo este tipo de modelos donde se tiene que la data observacional muestra que tenemos un aproximado de 95% de materia, bueno, de energía o componentes del universo desconocidos, llamados materia oscura o energía oscura. Recordemos que el término oscuro dentro de la parte cosmológica implica desconocido, o por saber, mejor dicho, ¿no? Mientras que la materia ordinaria solamente ocupa cerca del 5% de lo que conocemos, ¿no? Luego de ello, bueno, he intentado plantear cuál ha sido el marco en el cual hemos trabajado. Hemos trabajado partiendo de la relatividad general, considerando dos propiedades fundamentales del universo a escala cosmológica, a partir de los 200 megaparsec. Estas dos condiciones son la homogeneidad y la isotropía. La homogeneidad tiene que ver con que si alguna, bueno, vamos a decirlo así, persona se ubica en algún lugar del universo y llega a ver lo mismo, esa es la homogeneidad. Y si hablamos de isotropía es que si una persona se ubica en un lugar del universo y mira en distintas direcciones, un efecto de rotación, va a seguir viendo lo mismo. Entonces eso tiene que ver con la homogeneidad y con la isotropía. Bueno, hemos utilizado nosotros la ecuación de Einstein, universalmente conocida creo por todos, en donde vamos a relacionar la parte geométrica con la parte energética, ¿no? La parte que tiene que ver con la dinámica del universo, con la parte que tiene que ver con los componentes estrictos del universo de energía-momento. Ahora, ¿por qué llamarle holográfico? Es una gran pregunta. ¿O a qué llamarle universos con características holográficas? Bueno, esto tiene que ver más que nada con la utilización de este principio. Este principio Gerard Titov, Leonard Sansky y Jacob Eckstein plantean, año 1990 por ahí, plantean un enunciado que tiene que ver con que nosotros podemos estudiar las características que suceden en una determinada región a partir de las condiciones de su borde y a partir del área de este determinado borde. Entonces, como dice por aquí, los números de grados de libertad en un sistema acotado, ¿no? Limitado, evidentemente, deben ser finitos, ¿sí? Finitos, deben ser una cantidad fija, bueno, finita, perdón, y finalmente deben estar relacionados con el área del borde. Este fenómeno ha sido extraído fundamentalmente, o la idea ha sido extraída fundamentalmente del estudio de la entropía de los agujeros negros. La entropía de los agujeros negros evidentemente ha llevado al estudio de escalas mucho mayores que se trata de aplicar en distintas áreas, en este caso en escalas cosmológicas que tienen que ver con modelos de universo. Lo que pasa es que cuando hablamos de modelos de universo tenemos que concentrarnos en que los modelos de universo tienen que cumplir con ciertas condiciones que ya tenemos como resultado de toda la data observacional que presentamos. Entonces esas características tienen que ser manifiestas en este tipo de sistemas, en este tipo de universos, perdón. Bueno, en la literatura se habla, y eso sí hay que tener bastante presente, de que se habla de distintos tipos de modelos de energía oscura. Nosotros vamos a hablar de uno en particular, que tiene que ver con la energía oscura de tipo holográfica, pero enmarcada dentro de una cierta característica. ¿Por qué razón? Porque la energía oscura como tal, holográfica, tiene distintos modelos, y parte de esto, parte de un límite que tenemos aquí, un cutoff. Este límite que asumimos como igualdad en este caso, cuando se llega ya a maximizar este valor, dice que la densidad de energía oscura, o densidad, bueno, del vacío, tiene que ver fundamentalmente con una constante, con la masa de Planck y con una cierta longitud. Muchos hablan de la proporcionalidad de esta longitud L a la menos 2. Este L justamente es el que toma el rol o el papel importante en la característica holográfica. Se han atribuido que esto tiene que ver fundamentalmente con la medida o con el tamaño del horizonte de partículas. Al hacer ese modelo, bueno, calza perfectamente con ciertas características, sin embargo, se quita la particularidad de que el universo actualmente está acelerando, por eso que se descarta ese tipo de modelo. Luego de eso se habla de la famosa longitud o medida de Hubble, que está asociado fundamentalmente al horizonte de sucesos, ¿sí? A la medida del horizonte de sucesos. Y también, bueno, tiene buenos resultados, sin embargo, no presenta, o mejor dicho, no explica la relación de causalidad. Y una que en la actualidad, diremos actualidad, pero en realidad el año 2008, 2005, bueno, 2005 más o menos, viene proponiéndose distintos modelos que tienen que ver con esto, donde este L es proporcional y se establece como una razón que tiene que ver con el escalar de Ricci. Este escalar de Ricci toma cierto protagonismo aquí, dado de que este sí, además de las cuestiones anteriores, que bueno, vamos a ir describiendo, también permite o no presenta en todo caso contradicciones con respecto a la causalidad, al principio de causalidad. Entonces, por eso que nosotros utilizamos esto. Evidentemente, este escalar de Ricci va a depender del tipo de métrica que usemos en el universo que nos encontremos. Entonces, nosotros en particular vamos a hablar de un tipo de universo característico llamado Prima Elementary Robinson Walker, y de tal manera que se tiene esta expresión para el escalar de Ricci. De tal forma que esto alivia dos problemas. Uno que tiene que ver con el ajuste a los datos observacionales, que ya dijimos que es un buen ajuste, y por otro lado alivia lo que se conoce como problema de coincidencia. El problema de coincidencia tiene que ver fundamentalmente con que las densidades materiales o de los componentes materiales del universo, estamos hablando de energía oscura y de materia oscura, de ambos son del mismo orden. Entonces, en la ciencia han dejado esa pregunta, los científicos, abierta, diciendo, ¿por qué razón sucede esa relación en donde estos dos de alguna manera son del mismo orden? ¿Qué establece? ¿Qué condiciones? Y para eso tenemos que tener un principio de causalidad. Eso es justamente lo que se busca tratar de explicar a través de este modelo. Bueno, el modelo se da de esta forma. Es un modelo, como ya ustedes han visto, ha sido propuesto abiertamente en un artículo. Sin embargo, nosotros hemos explorado la mayor cantidad de posibilidades con respecto a ello, a partir de una energía oscura de tipo holográfica que depende del escalar de Ricci, y evidentemente con ciertas características particulares que nosotros estamos estudiando. Bueno, el universo espacialmente plano de Freeman Elementary Robinson Walker se muestra de esta manera, con esta métrica. La introducimos en la ecuación de Einstein que antes, hace un momento comentamos, y obtenemos esta expresión. Noten por favor que esta expresión, todos, tiene que ver fundamentalmente con el parámetro de Hubble, o bueno, con la tasa de expansión de Hubble, y con lo que se conoce como la densidad y la presión, que son característicos de cada tipo de componente del universo. Cada tipo de componente del universo evidentemente presenta una característica densidad y una característica presión. Y eso es lo que nosotros vamos a estudiar aquí. Estas dos expresiones que se muestran aquí son llamadas las ecuaciones de Friedman, ¿no? Anexado a ello, bueno, también tenemos la ecuación de conservación de tensor de energía-momentum, que bajo esta métrica y bajo las condiciones anteriormente mencionadas, se logra obtener esta expresión que se muestra aquí en la expresión 5. Además de ello, vamos a utilizar, bueno, las coordenadas geometrizadas. Evidentemente las expresiones constantes las vamos a hacer iguales a 1. Y por otro lado, vamos a utilizar que la presión tiene la ecuación de estado barotrópico. La ecuación de estado barotrópico es una ecuación que presenta la característica en donde la presión depende linealmente de la densidad, a partir, evidentemente, de un valor. Ahora, este omega que se muestra aquí, muchos admiten como un valor constante. Sin embargo, para esta investigación, dadas las condiciones en las cuales estamos estudiando, vamos a admitirlo como una ecuación o como un parámetro a evaluar, ¿no? Una variable. ¿Cuáles son los escenarios que hasta ahora se han estudiado? Bueno, fundamentalmente dos escenarios. Hay muchas publicaciones acerca de estos temas. Sin embargo, hemos tenido a bien clasificarlo en dos tipos de escenarios. Un escenario donde no existe interacción y otros escenarios donde existe interacción, como son los que se muestran aquí. Donde no hay interacción, bueno, este sistema de ecuaciones no se complica mucho. Fundamentalmente hablan de dos tipos de materiales que son los predominantes en el universo. Por un lado tenemos la materia oscura, llamada materia oscura fría, bueno, cold dark matter, y por otro lado tenemos la energía oscura de tipo holográfica, ¿no? Bueno, teniendo esas características y no considerando la interacción, se llegan a resultados muy viables, rápidamente. Mientras que si consideramos interacción e introducimos un término de interacción, vamos a encontrar algunos resultados que sí son evaluados, son estudiados por distintas investigaciones, como son los que se muestran aquí. Bueno, en un análisis general de nuestro modelo, ahora sí pretendo mostrar el modelo que hemos estudiado, nosotros tenemos que considerar, hemos tenido a bien considerar la apertura total al modelo. Es decir, cuando usualmente se estudia este tipo de esquemas o este tipo de escenarios, este tipo de universos, casi siempre se habla de los dos componentes predominantes, es decir, la materia oscura y la energía oscura. Sin embargo, nosotros vamos a establecer que existen todos los componentes, bueno, o lo que predominan en mayor medida, como son la materia bariónica. la materia bariónica, la radiación, la energía oscura fría y, perdón, la materia oscura fría y la energía oscura. Bueno, como notarán aquí, también hemos considerado una densidad de energía que tiene que ver con el sector oscuro, y esto va a ser fundamentalmente asociado porque ya existen publicaciones para poder comparar nuestros resultados. Bueno, en el caso de los escenarios de interacción, verán aquí que está un gamma, y este gamma justamente va a ser nuestra definición. Bueno, hemos obtenido una expresión también que tiene que ver con la densidad de energía oscura holográfica, que está en función de la cantidad energética del universo, y eso es lo particular o lo peculiar de este modelo. Bueno, se admiten algunas soluciones, pero verán que en el caso del sector oscuro, bueno, lo que tiene que ver con los componentes oscuros, fundamentalmente, el gamma es una función. Y este gamma hemos propuesto bajo distintos modelos. Bueno, tomando en cuenta los distintos modelos ya estudiados aquí en estas dos publicaciones. Hay muchos más, evidentemente, pero estos como que acogen a todo, o la gran mayoría, perdón. Bueno, aquí tenemos una expresión, una ecuación diferencial de segundo orden. Como notarán ustedes, es para la densidad de energía en el sector oscuro. Bueno, distintos valores para distintos parámetros, perdón, para distintas interacciones. Hemos obtenido también la solución de la densidad, que justamente vamos a compararlo en un momento, con el modelo aceptado hasta el momento, que es el modelo cosmológico estándar. También hemos obtenido la ecuación para el parámetro de estado. El parámetro de estado fundamentalmente está asociado a que nosotros conocemos cuál es el comportamiento de los distintos tipos de materiales. Como les decía, es característico. Por ejemplo, en el caso de la materia se conoce que este omega vale 0. Y en el caso de la radiación se conoce que esto vale 1/3, bajo ciertas condiciones, evidentemente. Bueno, aquí tenemos el parámetro de estado que estamos comparando nosotros a partir de los modelos de interacción que hemos propuesto con los datos obtenidos a partir del estudio de estos modelos, porque ya hemos dicho que estamos comparando con la particularidad, con la peculiaridad de que los modelos ya han sido estudiados, pero sin integrar los componentes totales del universo, solamente se han integrado los componentes oscuros, y estamos viendo un FITI, ¿no? Por ahí un ajuste. Nosotros lo hemos comparado con el modelo aceptado hasta ahora, que es el lambda Coulter matter, ¿no? Que es el modelo cosmológico estándar hasta el momento. Bueno, como notarán, de cierta manera nosotros obtenemos una característica aquí, en el sentido de que está evolucionando el componente energético oscuro a medida que interacciona con la materia oscura, ¿no? Hay una componente aquí de interacción. Para el modelo lambda Coulter matter no, pues, ¿no? Para el modelo lambda Coulter matter el omega para la energía oscura es -1. Ese componente de aceleración justamente, se ingresa a mano, ¿no? En el caso del parámetro de coincidencia, que justamente era uno de los problemas para nosotros. Ahora, la pregunta es, ¿y por qué radica o por qué es un problema? Bueno, era un problema porque si ustedes notan aquí, cuando estudiamos el modelo lambda Coulter matter, este valor tiende a ser 0. Eso implicaría que la densidad de energía oscura tendría que ser un componente que va creciendo, creciendo, creciendo infinitamente. Bueno, explota. Entonces, para nosotros, bueno, de acuerdo a las observaciones, de acuerdo a los modelos que hay, esto tiene que tender a un valor tentativamente plano, tentativamente constante, ¿no? Entonces, eso es lo que se logra obtener a partir de estos modelos con los datos asociados a las distintas investigaciones que he mostrado. Igualmente, para el parámetro de desaceleración, recuerden que este parámetro de desaceleración tiene que ver fundamentalmente con que se creía que el universo desaceleraba, pero sabemos que acelera, por lo tanto se niega, y esto es de signo negativo. También no tiene un comportamiento análogo al lambda Coulter matter, que es el modelo aceptado. Bueno, algunas conclusiones que puedo mostrar a partir del estudio de este modelo. Este modelo ha tenido un modelo teórico muy extenso del universo, donde se presenta 3 tipos de universo a partir de las distintas interacciones que hay. Se incluye el principio holográfico dentro de la característica o dentro de del componente energético oscuro, que es el predominante en la actualidad. Se estudia todos los materiales o todos los componentes inmersos en el universo. Hablamos de bariones, radiación, energía oscura, materia oscura fría. Y evidentemente obtenemos las funciones para cada uno de estos parámetros, que era nuestro especial interés desde el principio. También hemos propuesto un análisis gráfico de estos modelos que estamos evaluando con el modelo lambda Coulter matter, que ya les decía que es el modelo aceptado actualmente, ¿no? Bueno, algunas actividades que hemos ido avanzando, y justamente esa es también parte de la muestra que voy a hacer en a continuación, es de que podemos hacer un análisis, bueno, estamos haciendo en realidad, un contraste con los escenarios a partir de la data observacional que tenemos, las supernovas tipo 1A, los cronómetros cósmicos, el BAO, el SIMB, usando la estadística bayesiana, que es una estadística de tipo predictivo, bueno, análisis de escenarios. Y por otro lado, tenemos que también ajustar los valores, evidentemente comparando si estos valores son acertados o no, o responden en gran medida al modelo, comparándolo con lambda quadrat. Como les decía, tenemos algunos artículos para su interés. De repente a alguno le interesa el tema. Este ha sido ya, bueno, de alguna manera los alcances que hemos ido teniendo, hemos ido publicando. Uno de ellos es el primero. Y el otro nos salió hace mucho, inicios de este año. Hemos podido publicar una comparación bayesiana a partir de la estadística. Claro, no hemos analizado todos los datos, pero gran parte de ellos sí estamos analizándolo. A partir de supernovas, a partir de BAO, a partir de SIMB, a partir de cronómetros cósmicos, ¿no? Evidentemente para las variones, para radiación, para energía oscura y para la materia oscura, ¿no? Bueno, finalmente quiero agradecer al grupo de Cosmología y Partículas Elementales, que fue fundamentalmente los que financiaron, junto con el Vicerrectorado de Investigación y Posgrado de la Universidad de Bio Bio, los que financiaron este tipo de investigación. Y bueno, eso venía a mostrarles, agradecerles mucho por su atención y estoy presto a las interrogantes si existiese. Aquí están algunos datos de mi persona, bueno, si quieren contactarse. Bueno, gracias por su atención.
Muchas gracias, Carlos. ¿Alguna pregunta para Carlos Rodríguez Benítez? Muy bien. Bueno, andamos justo a la hora de término de esta sesión. Agradecemos a todos los oradores. Thanks to all the speakers. Y pues pasamos a la siguiente sesión. Adelante, José.
No, que había una pregunta ahí de Ashish.
Y una pregunta, sí, ya veo una mano ahora sí. A ver, sí, la pregunta, Ashish.
Yeah, I have one question. So in your proposed model, have you explored upper and lower bound on the equation of state parameter, which will result in inflationary cosmology in your proposed model?
¿La inflación cósmica si lo hemos propuesto dentro del modelo?
Yeah, in your model, yeah, exactly. So because there has to be some bound on the equation of state parameters so that the inflation can take place in your model, right?
No estrictamente lo hemos incluido porque nosotros estamos estudiando fundamentalmente el universo tardío, épocas tardías, actuales y futuras dentro del modelo. Partes iniciales del universo y su evolución, vamos a incluirla. Recordemos que para ello tenemos que estudiar perturbaciones de la métrica y eso estamos en un proceso de exploración, porque el incluir el principio holográfico genera cierto caos en algunos puntos.
Un poco la pregunta también sería en el sentido de que si el modelo puede incluir, o sea, no necesariamente que ya lo incluya, pero si no sería muy difícil incluir el proceso de inflación.
Claro, sí tendemos a incluir porque estamos evaluando con la data del SIMB. De la data del SIMB hemos utilizado solamente un punto, pero nosotros sí estamos en ese alcance, queremos hacerlo, la verdad. Estamos tratando de ver a partir de la perturbación de la métrica, ¿no? Y tratar de incluir la inflación cósmica como un estudio.
Muy bien, gracias. So, did that answer your question, Ashish?
Actually, I could not understand it.
Okay, well.
Thank you.
Okay, in the coffee break, there are rooms where you can try to have a chat.
Yes, there will be more time for discussion.
Okay, thank you. Entonces, adelante, José.
Right, so we are at the coffee break. Well, no, sorry. We have a tribute to Dr. Salvador Carrillo, who recently passed away. So Dr. Cristina Oropesa will present that.
Hi, yes, hi everyone. I'm just going to share. We gathered some pictures of Salvador, and so I would like to have that as a background while I speak. If you allow me, I've prepared some words, but I've prepared them in Spanish.
Cristina, sorry to interrupt you. Just to remind everybody that Salvador was our president of the division while he suddenly passed away.
Yeah, that's right. Okay, so yeah, so I've prepared a few words, but I will give them in Spanish. So I will switch now. Ni el fuego, ni el viento, ni el nacimiento, ni la muerte pueden borrar nuestras buenas acciones. Al final, solo 3 cosas importan: cuánto amaste, con qué gentileza viviste y con qué gracia dejaste ir las cosas que no eran para ti. Enseñe esta triple verdad a todos: un corazón generoso, un discurso amable y una vida de servicio y compasión son las cosas que renuevan la humanidad. Frase budista. Poco más de 2 meses han pasado ya desde la partida de nuestro querido amigo y colega Salvador Carrillo. 2 meses y aún no logramos dimensionar el duro golpe de la pérdida en lo personal, lo emocional y lo académico. El comité organizador me pidió que compartiera con ustedes unas palabras sobre quien fuera mi mentor, mi amigo, un ser humano noble, entregado a su familia y a su trabajo, que daba todo por sus estudiantes y luchaba por los más vulnerables. Un hombre que contagiaba alegría y también su entusiasmo y amor por la ciencia a los más jóvenes. Es difícil tratar de resumir la vida de Salvador. Como muchos de ustedes seguramente saben, Salvador le entraba a todo. Estoy segura que algo se me pasará, pero confío en que en cada uno de ustedes hay un recuerdo, un sentimiento que ayudarán a completar el rompecabezas. Salvador estudió Ingeniería Física en la Universidad Iberoamericana, Ciudad de México. Se tituló en 1990 con un trabajo sobre la factibilidad de construir un péndulo de Foucault en las instalaciones de la Ibero, realizado en conjunto con Fabiola Vázquez, conocida de muchos de ustedes, su compañera de vida. Muchos años más tarde vería realizado ese proyecto con la instalación en 2008 de un péndulo de Foucault en la Biblioteca Francisco Javier Clavijero de la Ibero, una de las más importantes del país. Sus estudios de maestría y doctorado en ciencias, con especialidad en física, los realizó en el CIMBESTAB, este último bajo la dirección de Alberto Sánchez y Héctor Méndez. En el año 2000 entró a trabajar a la Ibero como académico de tiempo completo. Fue director interino del Departamento de Física y Matemáticas, así como jefe de los laboratorios. Colaboró en el experimento E831, también conocido como Focus de Fermilab, y después en el experimento CDF del Tevatron en ese mismo laboratorio. En 2006 logró incorporar a la Ibero al experimento CMS del LHC. Hace 4 años comenzó a colaborar con el grupo de detectores de muones RPC del experimento CMS, en donde tuvo diversas responsabilidades, contribuyendo a la consolidación del grupo mexicano dentro de este grupo. En la Ibero participó en 2007 en una convocatoria para el fortalecimiento de infraestructura con una propuesta para armar un laboratorio para la construcción de detectores RPC en la Ibero. Ganó, y ahora ese laboratorio es una realidad. Su sueño era certificar este laboratorio para que se convirtiera en un sitio de ensamblado de RPCs para el upgrade de CMS y que además pudieran desarrollarse tecnologías para aplicaciones en arqueología y volcanes. Sus colaboradores más cercanos de la Ibero, la UAP y el CIMBESTAB seguimos trabajando para mantener vivo su legado. Además de su faceta como investigador consolidado, SNI 2, con un gran número de publicaciones, citas y estudiantes de posgrado, Salvador fue un incansable promotor de la equidad educativa y un ferviente luchador por la justicia social y defensor de las causas indígenas. Compartió sus saberes y supo escuchar a las comunidades con las que colaboraba. Enseñó y aprendió. Vienen a mi mente 2 instituciones con las cuales trabajó muy de cerca: el Instituto Intercultural Ñoñó y el Instituto Superior Intercultural Ayuc, el ICIA del Sistema Universitario Jesuita. Convencido de la importancia de la divulgación de la ciencia, Salvador fue impulsor y coordinador de eventos dirigidos a preuniversitarios, como las masterclasses y los días de rayos cósmicos. También participaba en eventos dirigidos al público en general, como las noches de las estrellas. Y de hecho, fue gracias a una idea suya que se instaló en la Ibero un sistema solar a escala como exposición permanente. Fue representante de la Ibero ante la Sociedad Mexicana de Física. Coordinó durante varios años los esfuerzos para los veranos científicos experimentales de nuestra área. Fue vice y presidente de nuestra división. Es sin duda alguna una gran pérdida, pero también nos deja muchas enseñanzas. Hasta pronto, querido Salvador. Gracias por tanto. Gracias por compartirte con nosotros. Gracias por todo. Muchas gracias por su tiempo. No sé si alguien quisiera compartir algo o no sé si ya no tengamos tiempo.
Muy bien, Cristina, muchas gracias. Definitivamente una gran pérdida para la comunidad aquí. No sé si alguien más quiera decir algo sobre Salvador. También está... pueden decir algo si quieren, por favor.
Hola. Perdón. Hola, perdón. Espero que se escuche. Soy
Sí,
Severino
adelante.
Soy Severino Carpintero. Perdón. Sí, solamente quería agradecer, pues, desde aquí a Salvador. Él, me apoyó mucho. Entonces, quiero agradecerle. Y qué bueno que le hacen un homenaje. Eso es todo. Gracias.
Gracias, Severiano. Muchas gracias.
Hola.
Sí, adelante.
Soy Fabiola.
Adelante, Fabiola.
Bueno, yo nada más quiero agradecerles a todos las muestras de cariño que tuvieron conmigo. Y bueno, pues aquí públicamente, gracias a todos. Y ya.
Claro. Sí, todos vamos a extrañar a Salvador. Compartió con muchos de nosotros. Gracias, Fabiola. ¿Alguien más o podemos pasar al descanso?
Solo agradecer a Cristina las palabras que preparó por Salvador. Definitivamente lo vamos a extrañar mucho y se queda en nuestro corazón para siempre.
Gracias.
Hola, pues yo también quiero comentar que Salvador aquí en Chiapas siempre nos apoyó. En especial él nos invitó al Día Internacional Cósmico, que ahora es una tradición aquí. Ha tenido mucha influencia para que tengamos más alumnos cada año. También aquí se escogió como sede para que se hiciera uno de los concursos de verano científicos y una de nuestras alumnas resultó ganadora, fue al DPyC, y ahora ya está estudiando por allá en Inglaterra, ¿no? Entonces él también pues nos apoyó mucho, en especial a mí. Él me dijo que le gustaría trabajar conmigo en la división y pues gracias a eso pues estamos aquí metidos en la organización y pues siguiendo tomando la estafeta, ¿no? Bueno, muchas gracias y recuerden que en el Coffee Break vamos a tener abierta la sesión principal, que es esta, para cualquiera que quiera platicar ahí, más los salones, los rooms, donde van a estar los speakers de la sesión. Gracias.
Muy bien, muy bien. Entonces yo creo que pasamos al break. A ver. Jesús, creo que ahora puedes crear los breakout. Ya están ahí, ¿no? Ok.
Listo, doctor, ya están activados.
Sí, entonces todos pueden ver en la parte de abajo, ¿verdad? Donde dice breakout rooms, creo que estoy viendo como 78, o cómo es. ¿Funciona por el nombre de la persona, Jesús?
Sí, exactamente. Ahorita están mostrando todos los usuarios que están, pero desplíguense en la parte inferior y les van a aparecer las salas, ya con el nombre de los doctores.
Ah, sí, okay. Okay, sorry, just to go into English. So if you click on the breakout rooms and then you scroll all the way down, you will see 3 or 4 dedicated Zoom rooms. And so if you want to discuss more about their talks, please join those rooms. Of course, we ask the speakers to be in that room. Thank you. And then we will come back to the main program at 11:31. So now it's okay. So like 15, 16 minutes we have in the break. Thank you. Just going to share that.
Hola, ¿hay alguien ahí?
Sí.
¿Es necesario grabar mientras está apagado esto?
A ver,
Simplemente por curiosidad, siguen grabando y suena chistoso que graben en seco,
sí.
¿no?
Yo creo que Jesús, ahorita puedes terminar la grabación y